In this video, I'd just like to unpack why the variation of parameters method works. In the previous video, we took a look at what all of this stuff means and kind of where it comes from. Let's see why this particular solution formula, in fact, is the correct way of finding the particular solution. So there's a couple of tidbits that we first of all need. We know that our system of equations that we're dealing with looks something like this. We have two differential equations. Let's call them dx dt and dy dt. And this one's going to be some potentially function multiple of x. So we've seen this coefficient, this p11, it's not actually been a function of time, it's been a constant. And for all intents and purposes, we're really only going to consider these coefficients to be constants, mainly because we don't really know how to solve a system of differential equations if this is not a constant. But I'm going to put these here as placeholders because this would work in theory if you could solve it with these functions of t and not just constants. So it'll look kind of like this. P11, the first one kind of corresponds to the first variable, so x, and then px2 times y, plus this non-homogeneous expression g1 of t. The second equation would be p21 of t times x plus p22 of t times y plus some other function of t. Now, as I've mentioned before, these are really only going to be considered for constants a, b, c, and d, because if they aren't constants, yeah, theoretically this method will work even if they aren't, but when you put functions in there, like, t squared or e to the t or sine of t, we don't really have a general way of solving those. So we're really going to focus on all the p's being constant. Okay, that's going to be our focus. This method works even if they're not, but it relies on the fact that you can find solutions. So the first step really is when we solve a non-homogeneous system. What we've learned in the past is that to solve the non-homogeneous, by the linearity principle and the superposition principle, we know that you first of all solve the homogeneous and we obtain what's called y sub h, which is y homogeneous. Now if this were for a single differential equation that looked something like this, going back a ways, if it were some function a of t times y plus b of t, just a single differential equation, then we would basically ignore the b of t term and we would solve this separable differential equation, find that homogeneous solution, and then secondly, but in our case this is not going to be little y sub h, this is going to be capital Y sub h, because remember we have a dx dt and a dy dt. So in our case, I'm going to write, we're going to find some vector solution y sub h, which will contain an x component and a y component. Now, in a lot of these systems, because when a, b, c, and d, when those guys are constants, we get two eigenvalues and two eigenvectors. We end up with usually two components to this solution, which we'll call y1 and y2. So if you recall solving a second order differential equation, you would find two values of r and you would sum those two solutions together. So we're going to have something like this. We're going to have k1 y1 plus k2 y2. And this is going to be k1 times what's inside of y1. Well, it's going to be the first x1 solution and the first y1 solution plus k2, and here we'll have x2 and y2. Okay, so that'll give us the homogeneous solution. And then the second step is to find a particular solution, a single particular solution to the non-homogeneous differential equation. So in our case, now we are actually going to consider this b of t, and usually we would do this by guess. We would try to pick a y that would look like this. So if this were a sine function, we would want to have a sine function in our y. But in general, this is going to be something that we'll call y sub p. Now this is a lot harder for systems because g1 and g2, these guys here, they don't need to be the same kind of function, meaning they don't even need to belong to periodic functions. One of them may be periodic and one of them may not be periodic. So you could have maybe sine and a quadratic. And so that gets a little bit more complex. So this is what we're after. So what should this be? Well, that's what this theorem proposes a solution for, and the answer is actually right up here. But how do we get that? Okay, well, let's start off with a couple of observations. First of all, we know that y1 and y2 are both solutions to the homogeneous system, which would be d capital Y dt. Remember that's just a container for the two individual derivatives, so that we don't have to write out two separate components. We just represent it as, hey, this is the vector of derivatives, and we'll write this as p of t times y. So those are solutions for this system right here. In other words, this means that if you take the derivative of the y1 vector, you get the same thing as taking the coefficients times y1. And same thing goes for y2, dy2 dt, its derivatives are going to be the same answers that you would get if you took p of t times y2. Okay, that's going to be useful for substitution purposes, as we'll soon see. And now what we're going to do is we're just going to, so that we don't have to have y1 and y2 as separate, right? Because right now, even though these are both their own systems, this is a system and this is a system, they're, again, represented as two separate equations. So I think what I'm going to go ahead and do is I'm going to go ahead and create this matrix, define X to be the matrix which will contain as its columns the two solutions that we've come up with over here, right? So if y1, as we've mentioned, contains x1 and y1, the first two solutions, and x2 or y capital Y2 contains the second two solutions, then all this is going to have in it is y1 is the column consisting of those two solution functions, and y2 is going to consist of x2 and little y2. And now we have this matrix that allows us to represent things in a different fashion. Okay. Next, the other thing that we know is that if you compare two matrices are only going to be equal if all their components are the same. So you could probably agree, I'm just going to do a little off to the side here to give you some intuition. If I compare the matrix consisting of these four components, the only way that it could be equal to this matrix over here, you'd probably agree, the only way these two matrices, the one on the left and the one on the right, could be equal is if the corresponding components are the same. So in other words, x over here has to be 1, and y over here has to be 4 in order for them to be the same. Okay, so the reason I say this is because this will actually allow me to represent capital X in a slightly different way. And what I think I'm going to go ahead and write here is to try to represent this system down here. So if I think about X as containing as its columns the solutions y1 and y2, then X prime would be the derivatives of those two solutions, right? So y1 prime and y2 prime. So you can imagine what these have in it. Well, all I'm trying to say here is that y1 prime is the x1 prime, y1 prime, and capital Y2 prime is little x2 prime, little y2 prime. And what do I know about y1 prime? Well, y1 prime is the same thing as dy1 dt. So I know that that's equal to p times y1, right? So as I set up here, if two matrices are equal, their corresponding components must be equal. So for this equal sign here to be true, y1 prime has to equal p times y1, which it does by that equation right there. And that's one column. And then the second column will be y2 prime. Well, what is it equal to? Well, it's equal to p of t times y2. Okay, so what that means is that I'm going to refer to this. Well, we know that this right here is x prime. And what is this over here? Well, this is going to be p times x, right? Because it's going to be p times y1 and p times y2. So I'm going to write that, represent that as p times x. There's a little bit of linear algebra here that we're not totally unpacking, but it is true that when you multiply two matrices, that the first matrix multiplies all the columns of the second matrix. So we'll kind of leave it at that. And there now we have an expression that we can work with. Now from earlier on, we know that one of the solutions to the homogeneous system is of the form yh equals k1 y1 plus k2 y2. Now from what we've learned in the past, this is not necessarily, in fact it's not going to work for the non-homogeneous case, because remember that when we solve the homogeneous case, we're assuming that we have that g of, essentially g of t has zeros in it. So this is really plus 0 over here, or plus a vector containing two zeros, I should say. Okay, so this is not going to work whenever these aren't zeros, because if you think about it, this expression plus this expression equals this. But then if you change these back to G1 and G2, now when you add these together, they're going to give you something more than what you have on the left. So what we're going to make a little assumption here. We're going to say that, this is probably going to still be part of the solution, but we're going to say that y sub p, that this particular solution is going to be some potentially non-constant multiple of y1. So I think I'm going to go ahead and call this u1 of t times y1 plus u2 of t times y2. Now, for the moment, this is going to seem like a strange assumption. And that's okay. We're not going to really get into the theory of this at the moment. But we're going to show that what you can do is you can find u1 and u2. So suppose that your particular solution will be some multiple summation of those two homogeneous solutions. Okay. So, in other words, this y particular, if I write this as a vector equation, I'm going to write it as follows. I'm going to say that this is going to be y1, y2, okay, a matrix with those as its columns, multiplied by the vector that contains u1 of t and u2 of t. So all I'm doing is I'm taking this scalar representation, what I have here, and I'm representing it as a product of two matrices. Okay, so what I really am saying is that yp is equal to, well, this whole thing here is just the X matrix, and this vector right here I'm just going to call U as the vector. Maybe I'll write it as a capital U. Okay, and let's just make sure that that's so far in. Yep, I think we're good. Okay, so what's the task? Well, the task is to really, under this assumption, if it's true, and it is, then we need to figure out what is U, right? We need to know what is U, not who are you, but what is U, right? That's what we are after right now. So somehow we need to be able to solve for U. With that said, we are almost done. Now we have just some substitutions to make here, and we can arrive at the conclusion of our theorem. So let me switch colors here, and let's go with a dark teal. So what do we know? Well, we know that if y sub p is a solution, then from our original non-homogeneous equation, namely this one right here, we know that the derivative of our particular solution is the P matrix times our particular solution plus those non-homogeneous expressions. So we know that the derivative of y sub p dt, if this is a solution, right? So don't worry too much about the strangeness of this assumption, because if it's too strange an assumption, then the mathematics isn't going to work out. The strange part is, well, how do you just decide to alter the constants? And I get it, but we're not going to worry about that right now. So this is equal to the P of t matrix times y, which we're calling y sub p. That's the solution that we're after, plus this G of t matrix. Okay, well, if I know already, based on my supposition here, and then my conclusion that y sub p equals x times u, the derivative of that will be the derivative of, well, by substitution, since y sub p equals xu, it's going to be the derivative of x times u. And I'm going to make the same substitution over here. I'm going to replace y sub p with x times u plus g of t. Okay, now I'm going to make an argument here, and this does require some justification, but recall that X, capital X matrix, has functions of time in it. Right? So it'll be, we didn't put them here, but these were all functions of time. These are all functions of time. So the derivative with respect to t is going to affect the components of the X matrix. U has these expressions u1 and u2 in it, which are potentially both functions of t. So these are both functions of t, and I'm going to make the argument by the product rule, even though we're working with matrices and vectors here. We're going to extend this. We're going to say, well, that would be the derivative of the first times the second plus the first times the derivative of the second equals P of t times x times u plus g of t. Now remember, what we're after here is we want to know, well, what should the U matrix be? What should the U1 and U2 be? Now, we are very, very close to being done here. One thing that we know from this equation is that x prime u and P of t times x times u, those are equal to one another. Those are equal to one another. Why are they equal to one another? Why are these two things equal? Well, the reason they're equal is because we already know that X, the X matrix, contains the homogeneous solutions. So we already know that the derivative of the homogeneous solutions is equal to P of t times the homogeneous solutions, right? Because once again, these just contain, this contains x1 prime, y1 prime, and so on, x2 prime, y2 prime. And we have our P matrix times x1, y1, x2, y2. So when we multiply this all out, you'll get x prime equals some value times x1, x2 prime equals some value times x2, and so on and so forth. So these are equal. Well, if I just multiply both sides by u, then they're still equal to each other. And what I'm trying to get at is that these are actually the same. They look kind of disguised because of this U matrix, but they both have it in the same position. So that must mean, therefore, it means therefore, x times U prime is equal to G. Okay, or G of T if you wish. Well, what do I do with this? Well, I need to solve for U. This equation I'll only be able to solve for U prime. Now, in the realm of working with matrices, there's no such thing as division by a matrix. Think about the equation 3x equals 12, an old algebraic equation. You could solve it by dividing by 3 on both sides, but another way to solve it is by multiplying by the inverse of 3. And in the realm of working with scalars, of working with numbers, and the inverse of a number is 1 over that number. So really this is just 1/3 times 3 instead of 3 divided by 3. So mathematically we think about it as the same operation, but in with matrices it matters. So this gives you 1, and you get 1x equals 3 inverse times 12, or 1/3 times 12, which gives you 4, and that all pans out nicely. So because we can't divide with matrices, what we can do is multiply both sides by the inverse of x. Okay, multiply by the inverse of x. And actually, let me do that on another line here. So we're going to multiply by x inverse here. I'm going to multiply by x inverse here. And you can think about these two as sort of canceling out. If you've taken linear algebra, then you might know that becomes what we call the identity matrix. And here we get x inverse times g of t. Well, what's inside of x inverse? From the previous video, we're going to just state the following, because this is a linear algebra result. The inverse of a matrix, if A is a matrix that has 4 components, A, B, C, D, then A inverse equals 1 over the product of the diagonals AD minus the product of the diagonals BC times DA, those two values get switched, negative B, negative C, as long as AD minus BC is not equal to 0. If it is, then you're dividing by 0, and that's a problem. Okay, so we're going to extend that result here. We're going to say, well, what would be the inverse of x under that condition? Well, x, remember, contains those 4 solution functions, x1, y1, x2, y2. And therefore, if we believe this and we apply this in a similar sense, we're not doing a lot of justification here, but x1 times y1, those are going to be functions instead of values. These are values, these are functions. Minus, oh, I'm sorry, this should be y2. x1, y2 minus y1, x2 times, again, switching x1 and y2, and then negating x2 and y1. This quantity right here is what we call the Ronskian. Okay, this is the Ronskian of x, and it cannot be equal to 0. Just that denominator, that's called the Ronskian. And the Ronskian of x cannot be equal to 0, because if it is, you get the same problem we had over here. Okay, great. So that means that u prime is going to equal 1 over the Ronskian of x times the function, or the matrix y2, negative x2, negative y1, x1, multiplied by g of t. Whatever g of t contains, it's two functions. One of them goes with dx dt, and one of them goes with dy dt. Now I'm omitting all the parenthesis of t notation here because it's going to get ridiculously detailed. So we know that all of these things are functions of t, but we're just going to leave that off. Now ultimately what we're after is not what, remember u prime, that contains the derivatives of the two functions that we need. We don't want the derivatives, right? We want the actual u1 and u2. So how do we get the antiderivatives of u1 prime and u2 prime? Well, we take the antiderivative. So to get u, we take it with respect to t, because remember these are all functions of t. U will equal the integral of the 1 over the Ronskian. And instead of writing this all out in this detail, we know that this right here is all part of x inverse. We know that this right here is the G matrix, and we're going to integrate that with respect to t. There it is. That gives us the components u1 and u2. What do we then do with them? Well, once we have u1 and u2, we can form our particular solution. Then y sub p equals u1 times y1 plus u2 times y2. We already have y sub h, and by the linearity principle, we know that the general solution of this system will be y equals the sum of the homogeneous and the particular. So that's what we need to do. We need to compute this U matrix, get those components, piece this all together, and then we will be done. So lots to unpack here, but again, the goal is just to have a good vision of how this stuff works, or at least have an intuition of how it all comes together.